Let's come to the fifth lecture. As usual, I hope you can all see now my file here. So what we wanted to start at the end of last time was to talk about stochastic processes in discrete time, and in particular, then stopping times, filtrations, and so on. And well, within the next two lectures, you will hopefully understand what I mean by all these words. But again, I would like to start with a small example to introduce stochastic processes. And then you immediately see why they are important for what we are planning to do with this term. This is example 2.12, which is the price process in the binomial model. Model. Right. Okay, I mean, this is something which will pop up quite often during the lecture, but I think it's good to take it as a guiding example to understand stochastic processes in our context. So, well, if we want to model some probabilistic objects, we need to have a probability space omega. So this is the sample space, and we take basically tensor project here of U and D. So these are just what I think of 1 and 2, and then you have T as our time horizon. And then the filtration, so the sigma algebra is just, I mean, this is a finite probability space, so we can just take the power set as our sigma algebra, and we have our time horizon as before. Usually, let's start with 0 up to time capital T. And now, well, we want to construct somehow the price process. For this, we consider here e to 1 to T. So independent and identical distributed random variables, JIs. And we want that these random variables, well, take two values. So they either go up, and then we assume that they take the value U with a probability P, or we go down. This means the JI takes the value D, and this is supposed to happen with a probability 1 minus P. So P is probability, and we want that both events can happen, so we have P equals between 1 and 0. Okay, okay. So what are U and D? So they are positive numbers, strictly bigger than 0. So we want that our prices are strictly positive, and they stay this way. Okay, and now we define our price process as, well, at time 0, this is the what we think of the time which you are currently. We have just a constant, and let's assume it's strictly positive. And then at the time t, the price is modeled by this process ST, which is supposed to be the product from t from 1 to t, and this is given by the upwards and downwards movements up to time t modeled by this random variable j multiplied with the time with the price we started with. Right. Let me. So how does the price looks like here? Let's just change the color. So we started the price 0. Then we go either up, down. So this is T1 U as U multiplied as 0 or D as 0, right? So that's and this is so this is T equal to 0, this is T equal to 1, and just to make another time step, this is T equal to 2. What? That's right. So we go either up again or we go down. Do the same, go up or we go down. So this means at time 2, the prices either went up twice. This is U to the power 2 multiplied as 0. Or we go up and down, or down and up. This leads to the same price, or we go twice down, right? So this is, then we can keep playing this until capital T, right? So this is our price process. So, and you see here, this gives you a stochastic process, right? So we have a sequence of random variables indexed by time. So for us, it's always time. So this is T in T is a stochastic process, and we make this formal with the definition in a second. Just that you have an example in mind before we go on, and this is the price process in the binomial model. All right. Okay, and this price process generates a flow of information. So this is what we thought about this. So this leads to flow of information, right? So if you know the prices up to time t, this gives you certain information about the market, and this is modeled by this filtration ft, which is given by the sigma algebra generated by all the prices from 0 or 1. I mean, since the first one is trivial, it makes not such a difference, up to time t. And here, t is in t. Okay. Wait. Let me here. So what is this? So this is flow, right? You have, this is again, it's a sequence of sigma algebras, which are given by, or generated by this price process S. All right. Okay. So this is our guiding example for today. And now we want to make this idea of a stochastic process and of this information flow more general. This is done in the next definition. Okay. So that's definition 2.13. Okay. Oh. All right. So first, family or okay. So just to recall, as I already said last time, I want not only to consider our index set T, I want to consider a more general index set I, to say, I mean, since it makes no difference for us, and I need this, for example, in the courses, advanced mathematical finance, where we talk about Jurassic process in continuous time. So there I don't want to do or recall all the definitions. And also, if you do more advanced probability theory, you will consider more general index set than this finite number of steps as we do in the more or less all the time in this course. So this is just the index that I want to use now. But if you say, okay, for me in this course, it's enough to replace all the time I with t, be my guest and do so. So a family of random variables. So this is just a family of random variables indexed by I. And I'm not super strict here, so I might allow in the future that these random variables take values in RD. So strictly speaking, this is then a random vector consisting of d random variables, but this is, I think, fine for us here to be not super strict. Is called Jurassic process. All right. So that's it. I mean, so there's is actually nothing very deep. It's just a name for a family of random variables. All right. Okay. Yeah. First definition. And now second, well, belonging, I mean, to this Jurassic process, you usually have a family of sigma algebras, as we have seen in our little example. So it's family of sigma algebras also indexed by I is called filtration. If they're increasing, right? So if you compare the sigma algebra at time s with the sigma algebra at time t, or of course 2 elements in I, then the sigma algebra at time t is bigger if t is bigger than s. Okay. Okay. That's called filtration. And another notion which will be omnipresent in our lecture is the notion of adaptedness. So Jurassic process xt is called adapted and well, strictly speaking to some filtration, so to the filtration f here, if my random variable xt, so the Jurassic process at time t, is measurable with respect to ft. Okay. All right. Okay. Okay. Just a little remark, which is rather obvious. Remark. So let's keep the numbers from the lecture notes. So every Jurassic process is, of course, adapted to the filtration which it generates. Right? So if we take a Jurassic process here, is adapted to fxt with xt is defined as, well, just the sigma algebra generated by this process. So if you take here all s, right? So every stochastic process, like the price process in the binomial model, generates a filtration. And of course, this process is adapted by the definition of the generated filtration here to this filtration. Right? And this is then often called here the natural filtration of X. Right? And it is the minimal filtration to which a process is generated. Right? So yeah. And if I'm not specifying in the future to which filtration the process is generated, then, well, I usually assume, I assume that it's adapted to its natural filtration. Okay. And now, for coming back to our example, let me make another small definition, which is 2.15, which is now, I want to extend the notion of probability by equipping a probability space with the filtration. So I want to consider a quadruple consisting of a probability space as usual. So I have a sample space, sigma algebra, and probability measure P. And I want to add here these the filtration, right? So if I add a filtration, I call this filter probability space. Space. Okay. If, obviously, if this here is a prop space, a probability space, and, well, this orange filtration here, yeah, it's a filtration. Is a filtration. Yeah. Okay. Other questions so far? As usual, please just ask questions in the chat if you would like to know something. I need a new page. Okay. So let us come back to our example, namely the binomial model. So that's example 216, which is nothing else than back to the binomial model. So, if we have now this price process here, let's go back to the model here. So if we have a process, price process, modeling a financial market, well, we want to be able to model trading strategies as well, right? So we want to be able to invest in a mathematical rigorous way in a market. And well, for the time being, let's start as simple as possible by considering a super simple trading strategy, namely, so what I want to be modeling, the trading strategy, which does the following. So I buy one asset. So I buy the asset for the price 0, right? So at time 0, I buy one of the risky share here modeled with the price process S, and then I have it, and then I want to sell it. Sell the asset if the price goes above some, well, constant C. Okay? So this is a limit order strategy. I buy at the current time 0, and then I keep the asset until it reaches a certain level, and if so, I sell, right? Okay, so but how do we want to do this mathematically? So we would like to sell at random, what it's called directly stopping time. Because you see, I mean, at time 0, I don't know when this event here will happen, right? So it might never happen. So we might keep the asset until the terminal at t, or it might happen at the first time, so at time 1. So we want to be able to sell at a certain time, which is given by this, let's call it tau, which is the infimum of t, well, in our index set, such that the time at tau t, so the first time the price process goes above the barrier C. Right? If that never happens, so if this set is empty, we set this just to infinity. Yeah. Okay. So we want to mathematically understand what this notion here means, because this is a naive trading strategy we want to be able to implement in our model. And this is, well, it's indicated already, this is it's called stopping time. And again, we want to make this little example more general by turning it and making the definition more general. So what we want to call a random variable, right? This is a random object, this time tau here. And we want that it takes values in our index at I or infinity, right? This is what we see here. So we either want to, we want to consider a random variable which, well, maps to the index set or to infinity. And this is then called stopping time. If and again, the stopping time is it's always with respect to some filtration. So, I will not, most of the time I will not say it, but I mean, it's always with respect to the filtration given our underlined filter probability space. And what we want to be able to do is we want to be able to decide at time t whether we have to stop or not. And this means given the information at time t, so the sigma algebra ft, we want to decide if tau is less or equal to t or not. Right. Okay. All right. Okay. And just to make my writing simpler, so the set of all stopping times is denoted by IS, right? This is our index set, and this is a deterministic set, and now we extend it to stopping times. And since we work most of the times with the set T, let me also introduce TS if E is equal to T. Yeah. Okay. So let us first characterize a bit the stopping times, and then let's consider some examples. And you can find also more examples on the next problem sheet. All right. Proposition 2.6, 2.18. As most of the time, as I said, we consider the set T. And there's a nice characterization when something's a stopping time if my index set is countable. In particular, finite, right? So if I have a finite set, it's countable. And then I have that tau is a stopping time if and only if I know at time t whether t is whether tau is equal to t or not. All right, so that's anyway. What does it mean? That's it, and we stay to t. So at time t, we can always decide based on the information given at time t whether we want to stop or not. Right? So stopping times are not allowed to look in the future. They can only act on the information given at time t. Well, okay, so this is a proposition. We need to prove it. All right. So there are two directions. It's an if and only if. So let's consider the first one. Assume that we have a stopping time. Then what do we observe? So for t, so we want to show that then tau equals to t is in ft. How do we do it? That's rather simple. It's just, so tau is equal to t. I mean, this event should be in ft. What is this? This is tau is less than t minus the set of the union of all s less or equal, s less or equal, no, strictly less, sorry, that's the whole point, strictly less than t given tau is less or equal than t, s, right? And here you see why you need to have a countable index set I, because you have here the union, and then only about countable many s. And this is important because sigma algebra is only stable under countable unions. If the moment you have uncountable many objects in your index set, you might explode outside your filtration or sigma algebra. So this is a stopping time. So this is in Fs. So this is in particular in Ft. So all these objects are in Ft. It means this whole thing here is in Ft. All right. So let's do the other direction. And this, let's assume that we know that tau equal to t is in Ft for all elements in the index set I. Okay. Again, we want now to verify that the defining property of a stopping time. So let's take t and I, and we want to show that tau is less or equal than t is in Ft. Well, this is nothing else than the union of all tau, all s in I, which are less or equal than t, of the event that tau is equal to s. And again, here you see where you need that you need to have a countable index set, so that this union, so this is by assumption Fs, we have an increasing sequence of filtration, so that's in Ft, means this is in Ft. All right. Other questions? Okay. Okay, let's go back to our guiding example. So, okay, always gets a new number, but it's basically the same example as we had before. So we have the price process in the, so back to example 212. So we are having the price process as in our binomial model. So yes, in tau is the price process in the model. Right. And we want to understand, okay, what are allowed stopping times? And the first trivial example is the constant times or stopping times, right? So if I want to decide to trade at a time s in this index set tau, well, this is stopping time. Because I can decide at time s that I want to stop at time s. Right? I mean, this is rather trivial, but let's check it to familiarize ourselves with the definition. So if I take any t and tau and the index set t, what do we know? So either, well, t is less than s, right? Then we have here the trivial, so the empty set, which means by the definition of a sigma algebra, this is an F0, and in particular, this is an Ft, or this is an either, or, well, S is less than T, so this is really then for all omega, this is the whole space, and the whole space is again by definition of a sigma algebra in F0, and this is then in particular in Ft. Right. All right, so it's well, now let's consider a more interesting example. So our limit order strategy, right? So we could take a general set K, and well, we want that this is a measurable set, right? So, I mean, to talk without, I mean, we always need to have to assume measurability, otherwise we could do anything, right? And the examples we were considered so far was we wanted to stop the moment the price process gets bigger than constant C. So, right. And then we have the stopping time. Let's call it tau k now, because it depends on this set k, which is the first time the process S enters the set k. Right? And I mean, before we had this set k here, where it means the first time that our price process goes above the barrier C. Right, and this is exactly what we have here. And now the claim is tau k is a stopping time. Right? I mean, intuitively, this makes sense, right? We can decide at time t whether the price process is above k, and we know that it has never been above c in the past, right? Indeed. So let's check the property of the stopping time. If we take now t in tau, and what do we have here? So tau k being less than t is just equal to the union of S and t intersected with, well, I don't know, just saying S has to be, let's write it like before. Right. S has to be less than t of the event S is equal then, or is, sorry, S is in K, right? And now this is an adapted process, so this is in Fs. And again, this means by the increasing property, so this is in Ft, right? So we check the property of the stopping time since F here is adapted. Okay. And this means here in this case, we consider the filtration generated by S as usually if we are not specifying it. Right. And now let me give you an example, which is not a stopping time. So this was the first hitting time of the process S hitting the set K. And now we want to consider the last time K. So the last time this process S with the set K, right? So consider tau tilde K, which is defined as the last time, so the primum of well, the primum of the time, so over time and for the last time S hits is in the set K, right? And now what we observe here is that obviously tau tilde K is not a stopping time. Make this red to emphasize this. Right. Right. I mean, this is obviously true because at time t, we cannot decide whether or not it was the last time of the price process S being inside the ZK, right? So even if it leaves, so the process leaves the ZK at some point, it might return to the ZK in the future. And this means, well, we cannot decide at the time t whether or not to exercise or to stop this process. And all right, so intuitively, it's rather clear what to do, but one needs to be careful and always check if something is a stopping time or not. Okay. All right. Lemma. So let us understand a bit how we can, or what operations are allowed between stopping times and which are not allowed. This is part of lemma 2.20. So let us take two stopping times, so tau and sigma, which are supposed to be stopping times. And here, I mean, the index does not need to be countable, so it can be a general index set. And then we take two stopping times. And what do we have? First, if we take the maximum, and this little v is just the maximum of the stopping time sigma and tau, and the minimum, right? This is the little head here of sigma and tau are stopping times. Okay. And okay, so taking the minimum and maximum is allowed and preserve the property of times being stopping times. Now, if sigma and tau are non-negative, and well, our index set has to be stable under addition, so closed under addition. Then, well, if we take the sum of two stopping times, it is again a stopping time. Okay. So these are all operations which, under the right, suitable conditions, leads to new stopping times. Again, we need to prove it. So let's do it. All right. Step first. So we want to show that the minimum and the maximum of two stopping times are stopping times. So let's take an element t and I, and what do we observe then? Well, what we want to show is that we can decide whether to stop or not with respect to the minimum of tau and sigma at time t, right? So this should be measurable with respect to ft. where the minimum is less than or less or equal than t if and only if sigma is less or equal than t or tau is less or equal than t. Okay. So this means this is a stopping time. Is a stopping time. And well, now we need to understand the maximum. And well, the maximum is less or equal than t if and only if sigma is less or equal than t and tau is less or equal than t. Okay. And well, these are both stopping times, so this is measurable with respect to ft. So this means sigma max tau is in SI. Okay, so that's it. And now we want to understand why the sum under the condition that we have non-negative stopping times and the set is stable under addition, right? Because if this is not stable under addition, then this is of course not well defined. So the sum of sigma and tau is not a stopping time because it's not well defined. But this is what we excluded by definition. So again, we want to consider an t and I. And for this, we define an auxiliary ft measurable random variables, tau prime, which is tau minimum t plus the indicator function of the event that tau is bigger than t, right? So the idea here is that if tau is bigger than t, we set the random variable tau prime to be t plus 1, right? And we define the same for sigma, so sigma min t plus indicator function of sigma being strictly bigger than t. Again, the same idea. The moment sigma is bigger than t, we set sigma prime to be t plus 1, right? And why is this ft measurable, right? This here is ft measurable, and this, right, because we take the minimum as ft measurable, so we are fine. Same for sigma prime. But now, this is why we played this little game here, introducing new random variables. Well, if we want to decide whether the sum of tau and sigma is less than t, well, this is the same event than tau prime plus sigma prime being less than t, right? Because the moment, well, 1 here is bigger than t, so one of these is bigger than t, so it's strictly bigger than t, then the sum is strictly bigger than t, and this here is then one of these random variables, tau prime and sigma prime, is set to t plus 1, so this is the case. And if they are less or equal than t, well, the minimum is just tau plus sigma, and sigma prime and tau prime are also just sigma and tau, right? So this is now of ft measurable, means the sum is ft measurable, and we are done. Okay. But as we have seen already, in the example before, not all operations are allowed or will lead to new stopping times, right? So just as a warning of 2 stopping times. Preserve the property of being a stopping time. Wait, let me make this red again. Right. So be careful. For example, so if you take tau minus sigma, or just tau minus a constant s, are not stopping times in general. All right. All right. Okay. And now, sorry. We can also consider, well, the sigma algebra. So far we considered filtration, which was a sequence of increasing sigma algebras. And now we can also consider, well, the sigma algebra with the information up to stopping time tau. This is the content of the next definition. So for tau being a stopping time here, the sigma algebra of the tau past, right? This just means the sigma algebra which contains the information up to the time tau is defined as f tau given by all events in the sigma algebra f such that A intersected with tau t is in ft for all tau in the index set. And well, this is indeed a sigma algebra, as you are invited to show on the next problem sheet. I have all these colors. We used it. Let me again come back to our guiding example. Which is now 2.23. So let us recall our stopping time tau. So stopping time tau in our example was the first time tau in t such that at the price process S here is above the constant C, right? And now we want to consider two events. The first one is A, which is the supremum of over time, so T and capital T of the process, S being bigger than t with c minus 5, and b is in t. So again, the supremum is supposed to be in c plus 5. Okay. And now, to make a little surface here, bleibt remark. Okay, there's a question, sorry, which asks if I going to prove remark 2.21. And there's nothing to prove here, I would say, because of course you could have always, this is not a general statement. I'm just saying in general, if you think about the difference of two stopping times, you will see that you can cook up examples. Examples mean really to construct a probability space on which this is not a stopping time. Of course, you can always also cook up an example where the difference is a stopping time, which is probably a rather trivial case. So this means here in general means it's not hard to cook up here examples which ensure that this is not a stopping time. Okay. But now the question from my side is, which of the events, or both, maybe both, is in the events A and B are in this sigma algebra of the tau past. So may I get some guesses from your side? So is A or B in the sigma algebra F tau? Just write A or B, what you think in the group chat. Okay, I got one feedback here. Somewhere else? Another A. Okay, there seems to be a consensus that A is in the sigma algebra tau of the tau parsed, and B is not. So this answer is correct. And now let's make this rigorous. So tau is this the claim. This claim is correct. So A is in the sigma algebra F tau. Well, why? Because if we consider, again, we need to check this. So let's consider T in the index set I. And what we want to show is that the intersection of A with the event tau less than T is in ft. Right, and this is, well, nothing else than tau less than t, right? So if at time tau, and tau is less than t, the price process was already above the barrier C, this means also the supremum was above the barrier C, and in particular above C minus 5, because CCSC is a non-negative or positive constant, right? And now tau is the stopping time. This is an ft. So tau stopping time. All right. And the second, well, let's claim, however, we cannot decide whether or not B was already the case. So the event B is not in the sigma algebra F tau, since we cannot decide up to time tau if S, T, and I will exceed T plus 5, right? So this means only because we know that the price process was above the barrier C, we cannot decide anything whether or not the price process will be above the barrier C plus 5 at some point. So you can, okay. Page. But we can investigate a bit more the properties of this sigma algebra F tau, and a very useful and natural property, as you might expect, is so if we take two stopping times, tau and sigma, and we assume they are ordered, so sigma is less or equal than t, then also the information generated up to time sigma is less or equal than the it's included in the information generated by tau. Right, so if the tau is always bigger stopping time, or almost surely bigger stopping time, then it also gives you more information up to this time. Okay. Again, let's prove it. Okay. So what do we want to do? So we want to show that, let's take an event in the sigma algebra F sigma, and we want to show that this is a element in the sigma algebra F tau as well. So first thing we want to know, so we take an element in the index set and we note that A intersected with sigma less or equal than T is in FT, right? This is just the definition of the sigma algebra F sigma. And this is the first thing we want to note. And the second thing we want to note is, well, since tau, so this is all sigma, and we can, if tau is a stopping time, so we know that the event tau being less or equal than t is in ft as well. Of stopping time. Right? And now we know as well that sigma is less or equal than tau. So this means if we want to check or decide whether the intersection of A with the event tau being less or equal than t is in ft, we can rewrite this as A intersected with the event sigma being less than t, right? This is a strictly bigger event than the event tau being bigger, less or equal than t, right? Because the stopping times are ordered. So we intersect first with the bigger set and then with the smaller one. So this changes nothing. And this means this is an ft, right? Because let's make this star and this star star. So this is in ft by star, and this is in ft by star star. All right. This was already the proof. Okay. Right. And if we talk about stopping times, as you have seen for the price process, what we want to do is we want to stop trading strategies or the price process itself. So we want to consider now stop processes as well. And this is also where this filtration sigma algebra with the tau parse comes into play. So if we consider okay, let's make it countable because we want to use the characterization here. So if we consider a countable finite set as an index set, and we assume that we have a stopping time, what is supposed to be strictly less than infinity, right? We allowed in principle that stopping times may take the value infinity, but here we want to have that it's finite almost surely, and we have a stochastic process. Let's call it x, indexed by I, which is adapted. Adapted process. Okay, sorry, it's an adapted stochastic process. Then it's a statement. So if I consider the stop process x at time tau is ft measurable. What is f tau? Well, just once let me write it down precisely. So this is principle a vector, so a random variable again, which is defined as the mapping omega maps to x at the stopping time evaluated at omega and then evaluated the process at time omega. So, right, this is just a composition of two functions, omega at tau and x. Both, right? And the one function is in omega and the other one is in tau. Okay. And well, not sorry. The claim is of course that this is right. This is important, right? The claim here is that the process stopped at time tau, so the random variable. So if I evaluate the process at time tau, this is f tau measurable. Okay, let's check this. Okay, okay, we want to check measurability, so let's take set A from the rel sigma algebra on R, plus. And that's it, R plus. And we take an T in the index set. And then what we want to show, okay, what we first want to know is that if I consider tau in the event tau equal to S, intersected with the pre-image of the process at time S of the set A, that's in F, right? Because, well, that's the stopping time, that's in Fs. And this is by the measurability of the adapted process here in Fs. Right. Here we need the countability because we use proposition 2.18. Okay. Right, this is, and so here. Hence, we get, consider now the pre-image of the process X at time tau of the event A, and intersected with tau in the event of tau being less or equal than T, right? And we want to check that this is in Ft. Well, this is nothing else than the union of all S over all S less or equal than T of tau being equal to S intersected with the pre-image of the process at time S of the set A. Right? And then by the arguments before, this is in tau T. And here again, we use the countability of the set I. Right? So this is actually, with this proof, it's rather crucial that we have this. So that means the set A is in F tau. All right. So if I consider the process stopped at time tau, so the random variable x tau, it's measurable with respect to the filtration of the tau past. Okay. All right. And now we want to introduce the processes which are very useful in the modeling of price processes in mathematical finance. And these are martingales. I mean, they appear in many other applications, but we of course, here care about the financial ones. So what we want to understand, I mean, there are a zoo of different probabilistic processes or heuristic processes, and they are all useful in some contexts. But in financial markets, we want to, I mean, they should be modeled at least to some extent related to fair games. I mean, it's not saying that they are pure, I mean, they're not a priori fair game, but they should be related to, well, these game theoretic ideas that we cannot make arbitrage, so that the market is to a certain amount fair. And this, I mean, is nicely captured by the notion of martingales, or related notions of super or sub martingales and so on. So what we want is we fix filtered probability space. I mean, this is what we have done already before. So we always assume we work on a filtered probability space, omega f. So this is our filtration. And this is our probability, right? So, and I is our index set. Okay, and well, as I said, if you don't want to think about continuous time and so on, you're invited to think of the index set we actually consider most of the time. So think of this finite time horizon, right, index from 0 to capital T. Okay. So let me directly start before coming to examples with the fundamental definition of Martingale. Yes. What? What? Definition 2.26. All right. What do we want to consider? We talk about stochastic processes. So martingales are stochastic processes. So consider here a stochastic process indexed by I. And what we do, at least in this course, we consider always real valued processes. And they are supposed to be adapted, right, with respect to our underlying filtration. Here, given by the filter probability space. And we want to make the assumption that it's integrable. So we want that the absolute value integrates to something less than infinity. And we assume this for all I, obviously. So that's our process of a given one. And now we call x. Tau is called martingale. If the conditional expectation xt given fts is exactly xs, right? So let us digest this. So what I mean, if we are at time s, so we have the information at time s, and we want to make the prediction of xt given this information at time s, well, this is the current state of the process, namely xs. Right? So in terms of a price process, with Martingale, this means the expectation of the price at time t, so future price t, is exactly the current price s, right? So it's as likely to go up than it is likely to be to go up, to go down, right? So the probability, or in average, you gain or lose nothing. and there are different time of games. So these are also sub-martingales. If the market works in favor of us, for us, right? So that means the expectation is that this game goes up. So if X models our game process, this means, or if we keep trading, our expectation is that we have more money at time t. And there's the super martingale. If the expectation goes down, right? So as in terms of a game, a super martingale is not good. And this I have to hold for all S, T, and I with. All right, let me mark this. So the martingale, sub-martingale, and super martingale. And just so to emphasize here, so if you want to check if a process is a martingale or not, you have to check 3 properties, right? So they are hidden one. The first one is you need to show that it's adapted to the filtration. The second one is you need to show that it's integrable at every time point. And the third one is, well, the basically defining property of martingale, super martingale, or sub martingale. All right, here we are. All right, so one trivial remark, but I think it's good that, well, one is aware of it in the following, is that every martingale is, well, by definition, sub and a super martingale. Right? So all the results or statements we prove for sub or super martingales, they are always also true for martingales. Right. So every martingale is also a sub and a super martingale. Right? Sounds easy. It is easy, but you should keep this in mind for what we are going to prove in the following. All right, to get some intuition, let's discuss some examples before studying properties and so on of martingales. So let me give you 3 examples, and I think you see others in the tutorials as well. So the first one is something you have already seen. Example 1 is the random walk. Here, martingale. Right? You can define random walks which are not martingales. And this is, I mean, what you have seen already. We call the example 2.9. Let me. So I will recall it for you now, but just to, I mean, this remark is more that you know, okay, you have seen it already, and you can go back in your notes to check that you have seen it. So let's consider, as in this example, random variables x1 to xn. they are independent and identically distributed random variables. And we assumed that the expected value of each of these random variables is equal to 0. For all I from 1 to n. Yeah. So I mean, in particular, if we take the conditional as the expected value, this means we assume that it's integral. And we set the filtration to be generated by the random variables, and to have filtration at time 0 as well, well, we set it to be the trivial one. And then the random walk was given by Sn, which is just the sum of these random variables x1 to xn. And we start with 0. And I am not doing the calculation again. I mean, as we did it already in this example 2.9. So what we have observed is that if we calculate the conditional expectation of Sn given Fn, we have that it's Sm. Right? This means, I mean, we have done everything here is just meaning this is a Martingale. So if you consider the process from 0 to capital N of Sn is a Martingale. Okay, why is this the case? Well, it's integrable, right? We assumed this basically here. It's adapted because we consider the filtration here is just generated by the process. So it's Sn is adapted to the filtration Fn. It's integrable because it's the sum of integral random variables, because we assumed this here. And we check the Martingale property, which is this one here. Right? So these are the 3 properties we wanted to check. Well, they're clearly fulfilled. So this random walk we considered is a Martingale. And now, well, you can easily turn this Martingale random walk into a sub or a super Martingale. So alternatively, if we assume that the random variable xi expected value less or equal than the 0, then the process is only, not only, and then the process is a super Martingale. And if you think of this as in terms of a game, so if you say xi are the profit or losses you make in the ith round of the game, where if the expected value in each round is 0, this is a fair game. If the expected value in each round is less or equal than 0, this is a game which is not in favor for you. So this is a super Martingale. Or if we assume that the expected value here goes up, so if you make in each round, well, in average some gains, so 1 to n, then this well, game is a favor for you. So you expect to make some profit, and then this is a super martingale. Right. Okay. All right. And well, why don't you finish this? So, it's not good. I mean, the explanation. So, you can look in the lecture notes. I mean, I added there some little calculation, or just check it yourself, right? That this is true what I claim here. All right. Thank you very much. Are there questions? Okay, then see you all next Thursday, where we keep talking about martingales and its properties and transforms. Bye.
Jemand hat noch eine Frage gehabt.
Okay. Zeigen wir Martingale-Konvergenzsätze. Okay, die Antwort ist nein. Der einfache Grund ist, weil wir Finanzmathematik auf dem endlichen Zeithorizont machen und dementsprechend kein Konvergenzverhalten brauchen, was irgendwie gegen unendlich geht. Wir machen Dupes-Ungleichung und Martingale-Transforms. Das ist das, was wir brauchen. Deswegen Dupe vor allem halt für Advanced Mathematical Finance, aber keine Konvergenzsätze. Ja, ihr müsst bis zur WT1 warten. Oder im Klenke gucken, das wäre einfach das nächste Kapitel. Also guckt im Buch auf Klenke, es ist nicht besonders schwer, aber ich brauche es nicht für den Kurs. Noch weitere Fragen? Okay. Ciao.